Our next speaker is Njesa Totty. Njesa is finishing up her PhD program in statistics, and she is also a graduate teaching assistant and conducting research on statistical applications in higher education. Today, she is going to talk about the newly developed R package, BootEd, that was designed to help teach bootstrapping methods in statistic courses. Thank you, Njesa. Go ahead.
All right. Okay. All right, so hopefully everyone can hear me well. So good afternoon, everyone. My name is Njesa Totty, and I am a PhD student at Oregon State University. Over the last 4 years of my graduate education, I've worked as a teaching assistant for statistics courses in my department. I've also been fortunate to work on curriculum development projects and special teaching assignments within my department. And these experiences have given me an interest in statistics education research and in developing methods to help students better understand and implement statistics. Today, I will be presenting a research project which pertains to teaching simple bootstrap intervals to introductory statistics students. Specifically, I will discuss the basic, percentile, and studentized bootstrap intervals. I will also give some information on how teachers can use R to perform simulations in the classroom, which can help students understand the assumptions behind bootstrap intervals and implement them responsibly. So why teach bootstrapping in the first place? Well, bootstrapping and other statistical computing methods have much support in the literature, and they are widely included in introductory and advanced statistics textbooks. Some examples are given in the first bullet here. Concerning the literature, a study conducted in 2012 found that the use of a randomization-based curriculum led to a higher retention of concepts after 4 months than using the consensus curriculum. Also, the use of simulations can lead students to actively and intelligently use the methods they are taught, which can increase how relevant a concept is to the student and how relevant it continues to be after they leave the classroom. Specifically, it has been noted that bootstrapping can fortify a student's understanding of concepts such as sampling distributions, and it paves the way for teaching inference on uncommon parameters. This actually agrees with the goal which was set for introductory statistics students in a recent report on statistics education. The guidelines for assessment and instruction in statistics education are published reports which set the framework for statistics education at the K-12 and collegiate levels. These reports have been endorsed by the American Statistical Association, and several well-known introductory statistics textbooks have credited them as advising their approach. Teaching bootstrapping can help students to understand and implement the basic ideas of statistical inference for a variety of settings. However, some misconceptions about the simple bootstrap exist, and this has led to concerns with teaching it to introductory statistics students. Some of the misconceptions listed here are discussed in a recent article by Robert Hayden. Our research focuses on assessing the assumptions and conditions behind these methods to determine if there are really fewer or no assumptions. Since these methods are increasing in popularity, it is possible that the simple bootstrap will be taught in introductory statistics courses outside of a statistics department or implemented in industry. So digging into these and other misconceptions about the simple bootstrap can ensure that these methods are catching on in a good way. So now I will give a brief introduction to simple bootstrapping and the basic, percentile, and studentized bootstrap intervals. This will be helpful for understanding some of the assumptions behind these methods and the simulation results obtained using R, which we'll discuss later. So this image here gives a visual representation of bootstrapping through simple random resampling. We take a random sample from the population of interest, and from that original sample, we resample about 1,000 times. Now, for each of these resamples, they are the same size as our original sample, and sampling is done with replacement. And these resamples are called the bootstrap resamples. From each bootstrap sample, we then calculate the statistic of interest, and these are called bootstrap sample statistics. And the bootstrap sample statistics make up the bootstrap distribution, and this can be used to estimate the sampling distribution of the original estimate. So how is this useful for constructing interval estimates? Suppose that we obtain an estimate, theta hat, of the population parameter theta using a random sample from the population. If we use just 1 point estimate to inform our knowledge about the population parameter, we ignore the variability from sample to sample. But we can construct an interval estimate, which will give us a range of plausible parameter values, taking into account the variability from sample to sample. But how do we estimate the variation in sample statistics without the sampling distribution? This is where the bootstrap distribution comes into play. Using the shifted sampling distribution, we can derive the form of a 95% equitailed interval for the parameter of interest. Since we do not actually have the shifted sampling distribution, we can use the shifted bootstrap distribution to estimate its quantiles. The basic percentile and studentized intervals estimate these quantiles in different ways. For the basic bootstrap interval, this is obtained by first noting that the pth quantile of the shifted sampling distribution can be expressed as the pth quantile of the sampling distribution minus the population parameter. The pth quantile of the shifted bootstrap distribution can be similarly expressed as the difference between the pth quantile of the bootstrap distribution and the original sample estimate. After a little algebra, we obtain the final statement given here for the form of the basic bootstrap interval. Here we implement a recommendation from section 2.2 of the Davison and Hinckley textbook referenced earlier to use the ordered values of the bootstrap distribution as determined by the product of the number of bootstrap samples and the quantiles of interest, and these values are assumed to be integers. If we additionally assume that the shifted sampling distribution is symmetric, then estimating its quantiles using the shifted bootstrap distribution gives a simpler confidence interval. After adjusting for symmetry, we obtain a final form for the bootstrap interval, which incorporates just the 0.025 and 0.975 quantiles of the bootstrap distribution. Here we again use the recommendation mentioned earlier to estimate these quantiles. Lastly, if we assume that the shifted sampling distribution is normal with mean 0 and variance sigma squared, we would obtain the normal approximation confidence limits given here in the second bullet. However, this assumption is not always valid, and in that case, we can use a bootstrap approximation instead. First, using the bootstrap statistics, we can obtain an estimate for the variance of our estimate. We can also construct a type of standardized bootstrap distribution, which can be used to approximate the quantiles of the standard normal distribution. In order to do this, we must estimate the variance of each bootstrap estimate. One option for accomplishing this, given in the second sub-item here, is to use a second-level bootstrap to estimate the variance of each bootstrap estimate. Suggestions for the number of second-level bootstraps found in the literature range from 10 to 50. This method is computationally intensive. If we have 1,000 bootstrap samples and we take 25 second-level bootstrap samples for each, that's 25,000 bootstrap procedures that must be completed just to obtain one interval. So what was the point of touching on the theoretical underpinnings of these methods, and where does R play into this? Well, if you notice, each of these intervals assumes something about the sampling distribution of the estimate. In the case of the basic bootstrap interval, we assume that the bootstrap distribution is a good estimate of the sampling distribution. For the percentile interval, we further assume that the sampling distribution is symmetric. Lastly, for the studentized interval, we assume that it is reasonable to use the form of the normal approximation confidence limits. This contradicts the misconception that they make fewer or no assumptions. Moreover, when these assumptions are not met, we may get invalid results, and we can use simulations in R to show this. For example, a point of concern discussed in the reference given here is that the bootstrap distribution is inconsistent as an estimate of the sampling distribution when the true parameter is on the boundary of the parameter space. Consider the population proportion, which can only take values between 0 and 1. We obtained 1,000 random samples, each set ranging from size 5 to 100 from a Bernoulli population, where the probability of success ranged from 0.1 to 0.9. The proportion of basic bootstrap intervals, which contain values that were negative or greater than 1, is given in this figure as a function of the sample size. So to clarify, for example, for this bar here, we took 1,000 random samples from a Bernoulli 0.1 population, each of size 15, and we constructed 1,000 basic bootstrap intervals. We then we used R to evaluate which of those bootstrap intervals contained values that were negative or greater than 1. We see that about 60% of those intervals did. When the true population proportion is close to 0 or 1, the proportion of intervals which contain values that are negative or greater than 1 is quite large. This proportion decreases as the sample size increases, but this does not happen quickly when the true parameter is near the boundary of the 0-1 interval. Well, it is actually known that the Z interval for the population proportion is similarly inappropriate when the probability of success is near 0 or 1. This is often translated into a condition that the number of successes or failures observed be larger than some cutoff. The results of this simulation show that this interval may have conditions which are similar to those of a more traditional method. Moreover, by performing simulations in R, students can see that ignoring the assumptions behind the basic bootstrap interval can be problematic. We also use simulation to assess the bootstrap distribution's ability to estimate the 0.95 quantile of the sampling distribution. 1,000 samples were obtained for each population and sample size combination. We hope to cover a variety of scenarios by assessing these different populations. So we sampled from 2 discrete and continuous population distributions, which are right skewed, and from a bell-shaped continuous distribution. Samples ranged in size from 10 to 1,000 by 10. The respective sampling distributions and bootstrap distributions were calculated for each parameter of interest, so here that would be the mean and the variance, and the relative change between the 0.95 quantile of the bootstrap distribution and the sampling distribution is plotted on the y-axis for varying sample sizes on the x-axis. In the case of the sample mean, which is known to have an approximately symmetric sampling distribution due to the central limit theorem, the results support using the quantiles of the bootstrap distribution as an estimate. We see that the relative change tends to be near 0, and more so as the sample size increases. However, for the variance, the results are less supported. There is some convergence as the sample size increases, but it is quite slow. Further work could be done to recreate these results using the ordered values of the bootstrap distribution rather than just the quantiles as suggested in the literature. This simulation, though, supports the idea that the underlying assumption of symmetry and the sampling distribution should not be overlooked when using the percentile interval. The last simulation that I will discuss today assesses the coverage proportions of these intervals. We began by selecting random samples from the same populations of interest used earlier, and these are given as the titles of the last 3 columns in this table. We also varied our sample size n and the number of bootstrap samples b. A summary of our findings is given in this table, and this has been shortened for visibility. Results indicate that the studentized bootstrap method captures the true population mean more closely to the theorized 95% of the time than other methods across the different sample sizes and population distributions. There's evidence of undercoverage for the basic and percentile bootstrap intervals as they systematically contain the population mean less than the desired 95% of the time. The severity of the undercoverage, though, depends mainly on the original sample size, but also on the number of bootstrap samples used. So we see that using R to teach bootstrapping can produce useful results about its underlying assumptions and its performance under a variety of scenarios, including those where assumptions are not met. While focusing on theoretical underpinnings can also produce useful results, teachers should consider if their students will better benefit from the use of statistical computing techniques for understanding these assumptions, especially for introductory statistics students who may not have a strong theoretical background. By discussing assumptions with students and exploring these assumptions and the performance of these intervals under different scenarios, students can leave the classroom with a solid understanding of how these methods should be used and when it is appropriate to use them. To that effect, we created the BootEd package with hopes that it would be easier to communicate the assumptions of simple bootstrap intervals to introductory statistics students. We also hope that teachers of these introductory statistics courses will be able to teach these methods more easily using this package. The functions in BootEd are independent of external R packages, so installing from GitHub only requires the use of the DevTools package. We also provide a vignette to help users get started with the package. When students implement the functions in BootEd, they are immediately made aware of the assumptions of the method and are encouraged to check conditions. There's also an option in our functions, only int, that produces only the interval, which can be useful for simulations. In fact, all of the simulations that I discussed today, were performed using the functions in BootEd. Plots are also given to assist in visualizing the results of bootstrapping and discussing any assumptions or conditions. This is a plot that's given from all of the functions. For other functions, for example, the studentized interval and the basic interval, the correct plots that would be needed to assess their assumptions are given as well. So the BootEd package is for teaching introductory statistics students simple bootstrap intervals with assumption checking and for performing simulations easily. While it is a starting point, it is by no means a replacement for the other great R packages that can be used for teaching and implementing bootstrapping, resampling, and other statistical computing techniques. Depending on course objectives and student backgrounds, the R packages listed here could be considered as preferable options, especially if more advanced sampling schemes or bootstrap methods are to be taught. We hope that BootEd will be a good and simple option for getting started with teaching bootstrapping to introductory statistics students. And if you happen to use the BootEd package, we would greatly appreciate any feedback or suggestions you may have. We're continually making improvements and additions to the package, and we're also working on a corresponding article for the package that goes into more detail. So I would like to acknowledge these people listed here, my advisors and senior instructors in our department, and I'll be happy to answer any questions that you have during the Q&A. Thank you.
Thank you so much, Njesa. That was excellent. I wish I would have had a simulation instruction or, like a lesson like that when I took stats at OSU.